Welcome, everyone. We will get started here shortly. We'll give a minute or two for everyone to get into the broadcast. I see we still have some people joining, so we'll give it another minute or so before we get started. All right, we're 2 minutes past the hour, so I see we still have people joining us. That's fine, but I'll go ahead and introduce today's topic. First of all, welcome to the first installment of our Whole Tomato Summer CodeFest. My name is Ben Schwank. I'm Chief of Staff for Whole Tomato, and I have the privilege of introducing today's webinar, which we'll kick off here in a minute. Our vision for the Summer CodeFest series is a series of short webinar presentations, less than an hour, for C++ programmers at all skill levels, covering a specific topic or theme of C++ programming to supplement your existing C++ skill set, or perhaps give you a glimpse into something new that you might want to explore incorporating into your own C++ coding and projects. And today's topic is next level concurrency, enhancing scalability with C++ 20. And that'll be presented by Whole Tomato's own Chris Gardner. Chris is our lead developer at Whole Tomato. He's been programming C++ for almost 2 decades, since he was 17. Chris is an extremely knowledgeable C++ programmer. He is a great instructor and communicator. He started in the realm of computer security, but eventually moved into game development. And I know that he is a passionate game developer and gamer himself, which is why he's such a great fit for his role as lead developer at Whole Tomato. I know you're going to get a lot out of his presentation today. If you're looking for the lineup of other Summer CodeFest sessions and topics, say that 5 times fast, we'll provide that link in chat to the full schedule as well as the registration. We have an intriguing series of topics and some interesting presenters over the coming weeks, which I think you'll really enjoy. Before we get started, I want to let you know that we will have time for Q&A at the end of the presentation. So please ask questions as they arise throughout the presentation, and we will circle back to those at the end and answer as many as we have time for. We will be moving through slides quickly with a lot of code examples. So in case you missed something or there's something you want to refer back to later, our slides are available as a virtual handout. You should see that as a link in the GoToWebinar handouts panel. And these webinars will be recorded and made available for rewatch. So if you need to drop or you want to circle back to something, you'll be able to. We will send those links out, those view links out to all registrants after the webinars conclude. Also, this webinar is sponsored by Whole Tomato. I'm sure many of you are familiar with or are even using Visual Assist, our Visual Studio extension for C++ and C# development, which our product manager, David, will tell you more about here in a moment. I did want to let everyone on the call know that we are rolling out a new academic program for Visual Assist. We're fully sponsoring schools, universities, and even online coding camps to make Visual Assist available to both instructors and students. So if you're in the educational world, either as an instructor or a student, and that sounds like something you'd be interested in, please reach out to us by sending us an email at sales@wholetomato.com, and we'll be happy to get that process started for you. We're excited about this new program, and we're eager to partner with educators and help raise up and bring more C++ developers into the industry. So with that all said, I'm going to hand things off to our product manager, David Millington, who's going to tell you more about Visual Assist and will lead us into today's topic presented by Chris. Go ahead, David.
Thanks, Ben, and hi, everyone. As Ben said, Wholetomato and Visual Assist is sponsoring this, and I just want to speak very quickly about what Visual Assist is before we get on to looking at concurrency with Chris, our lead developer. So next slide, please, Chris. Look, many of you I know probably already use Visual Assist because we largely advertise this to our existing audience. But Visual Assist is a productivity plugin for Visual Studio. Most recently, Visual Studio 2022, although we support a wide range of various versions. You can see a few screenshots there. It focuses heavily on navigation, refactoring, code generation, just a whole bunch of other tools. You can see on screen things like find references or finding symbols, or snippets that help you produce particular bits of code. On the top right, you can see a context menu that shows you more information about symbols, things like this. Basically anything useful that you would find as a C++ or C# developer, we try to do. Next slide, please, Chris. And is mostly well known in the 3 years of navigation, refactoring, and code generation, although we do a vast amount more. It's used on products that I know you will have used, very widely used in game development and so forth, and has a wide range of features. Now, this is not really about Visual Assist, it's about concurrency, so going to keep that introduction really short. You can always download a trial off our website at wholetomato.com or the Visual Studio Marketplace. It's written by developers. We are all devs, and we have written what we think is useful for developers. We try to have a real by developers for developers ethos, and that goes into the quality of the product as well, even things like its CPU usage and memory usage and that kind of thing. We want to create something we're proud of and that is a good citizen. So we believe it's a fine product. We hope you like it as well. And with that, I'll hand over to our lead developer. Chris, over to you, please.
Thank you, David and Ben. So today we're going to talk about, the title of the webinar is Enhancing Scalability with C++ 20, but most of the work you do in C++ 20 is really something that's been laid, the groundwork for has been laid in C++ 11. So we're going to be talking a lot about modern threading in general, and that's going to include a lot of topics from C++ 11 to 20. And then we're going to finish by talking about some of the things that are new in C++ 20. We wanted this talk to be accessible to a wide range of people. And I think that a refresher on multi-threading it makes a lot of sense in this context. So we're going to spend a good amount of time on that. And we'll start with what the value of multi-threading is. So of course, the main value of multi-threading is performance. Almost every application that we use makes use of multi-threading in some way or another. But of course, that's not just to increase their performance. Multi-threading also very usefully allows you to feel more responsive to user input. For example, if you don't have to hang an application's UI while a task completes, or you don't have to hang your game while you load in an area ahead of the player. This is all very important uses of multi-threading and very valid. So it's not just performance. It's also, being responsive. So even short tasks and stuff can be multi-threaded very, very effectively. So the value of multi-threading, again, is it's pretty clear. And personally, I've often heard from a lot of people that they wish specific applications made better use of multi-threading to increase their performance. I've heard a lot of complaints. If you're a gamer, you probably know what this feels like. Of course, there are a lot of difficulties with that. So as I said, this is going to be a lightning review of mostly C++ 11, and it's amazing. C++ 11 was such an important standard for C++. So again, I want this to be accessible to the widest possible audience. So a good portion of this webinar will be a review of the concurrency tools STL provides us up to C++20. And again, a great many of those tools came from C++11, which was such an impactful release. And personally, it changed the way that I thought about and wrote code. As C++ has been my main language, this was the first I was kind of shown these concepts, and it really made an impact on me. And most of its features, again, are still fully modern. So this will be a lightning review of C++ and hence modern threading. As we've done our quick, after we're done with our quick high-level overview, we'll cover what's new in C++20, but we are going to go pretty quick. All right, so let's take a look at this very, very optimal, of course, suboptimal implementation of a prime checking function. It takes a long, long time for big numbers. Let's say we wanted to use this function for some reason to find all the primes between two numbers. And we could do something like this. Very easily, we supply the find primes function with a beginning and an ending number, and it'll return a vector of all the primes it finds using our isPrime function. This will be our example of a slow workload, one that can easily be done concurrently, but you can imagine any slow workload. This will just be the example we use today. And this is important to go over, lambdas and std function. In the right image, I'm using a lambda expression to initialize a std function. And I'll be doing this type of thing a lot in this webinar. But in most cases, you can just imagine them as regular functions. Std function is basically a wrapper for a function pointer. So I'll be using lambda expressions a lot. If you need a refresher on lambdas, you are in luck, however, because David Millington will be going into detail in his webinar in a few days. So if you get tripped up here, try again once you've seen that. It's kind of an important prerequisite to this. All right, so let's get into our talk. Here's a code example of no threading. So here's an easy way to generate primes. We have a function find primes, which iterates through the set of integers. For each integer, it calls isPrime to determine if it has found a prime number or not. Once it's finished, again, it returns a vector of all the primes it found. To find all primes between 0 and 1 million, it takes 50 seconds on my laptop. Remember, this is using my slow isPrimes algorithm, so it could be running a lot faster, but it's good to run slow for this example. It was intentional, of course. Let's see the same example, but modified to run find primes in a separate thread. So this is the lowest level use of concurrency in C++, which is std thread. Of course, if you want to use create thread or something and be implementation specific, you could get lower level, but this is about as low as it goes. Std thread takes the find primes function and its parameters and then fires off a new thread immediately, which goes to work. And if you'll notice, in order to make this happen, I had to add a parameter to our find primes function and remove the return value. Std thread is pretty basic, and I won't provide any way of getting the return value back for our function. So to share the result with the main thread, our function needs to take a reference to the variable it can modify. Of course, we can then do other stuff in our main thread while that thread is busy, but we can't touch the primes variable until the other thread has finished working on it. To ensure the other thread is finished, we can call join. Join moves the execution of that thread into your current thread. Once join completes, we can safely use the primes variable. So basically, it completes the thread on the current thread. So once it's done, you can be sure that it's finished. And of course, we could use our free time. So we're still taking 50 seconds total, but we used our opportunity to do something in the main thread. Why not find more primes? Once I kick off the thread, I call find primes on the main thread. Now our two threads are currently engaged. Again, we have to make sure to call join before accessing the primes variable. But instead of doing more work, we could also split the work between a main and secondary thread. So that's taking less time. Here example, we're splitting two workloads between two threads. I have two results, and I start two threads, and make sure to join both threads before using their results. I took a guess here at how to split the workload. As I know the larger numbers take longer to check with isPrime. Ideally, we would have each thread complete around the same time, particularly for this low number of tasks. So that comes into a few tips. Generally, it's certainly a good idea to use threads. Generally, it's not a good idea to use threads to work on short tasks. There's a bit of overhead involved with creating threads and using threads. So do thread tasks which may take a while. So a task that may hang the thread for a while, for example, if you've got a UI, and then most of the time a task is quick, but sometimes it's not. you need to be ready to handle that. So you should be probably running it in a thread and keeping it from blocking, for example, your UI is a good example of when to use that. Load balancing can contribute a lot to speeding up your threading, as I will show. Keep an eye out for this when you don't have many individual tasks to run. In those cases, the total time that it takes to complete is equal to basically your longest task. So you wanna bring that longest task down. Just to quickly prove a point, I ran a couple of benchmarks over the previous example, and I can get an improvement of 5 seconds by moving slightly more work to thread 2. So that gives us basically what's optimal, because it took about 50 seconds before, takes about 25 seconds now. I could get a little bit less, but just shows you that 5 seconds for moving a couple, couple thousand to another thread is pretty significant. There's some drawbacks of this. This method of threading is fairly dangerous, as there isn't anything stopping you from reading the result early, for one. You also can't share the result very easily without also sharing the thread. So whoever's waiting on the result can be sure it's safe to read from. So for example, if I wanted to return the result from a function, even though the result wasn't fully completed, I would also have to return the thread, because they would need to be able to wait on that before accessing the actual variable. So they don't know when it's ready. But if we are just interested in knowing when our thread is finished, we can use atomics. If we want to protect ourselves from improperly accessing our data while the thread is working on it, we could use mutexes. So we'll talk a little bit about that. So unlike most types, std atomic types are safe to read and write between threads. There's certainly some subtlety to that that we won't have time to get into, memory ordering and such. But it's worth noting that atomics used in this simple way won't always be able to protect you in different situations. So let's update our find primes function again to use atomics to notify the main thread when we've finished. So here's our find primes function. It just takes an atomic and then sets it to true. Now we can hand our atomic over to the thread, and it can safely tell us when it's finished working. We can keep checking the isFinished variable in a loop with a short sleep to prevent the thread from busy waiting too bad. Std mutex is similar, but it's safer to use and comes with more restrictions. Std mutex allows you to safely control access to your variables that are shared between threads. In this case, we convert isFinished to a simple non-atomic bool, and we use std mutex to protect access to it by first locking before reading or writing. So this one thread is able to hold the lock only one thread is able to hold the lock to the mutex at one time. If someone tries to lock, it just waits until it can access until someone else unlocks it, and then it's able to get the lock. Below that, we have this code. We create the std mutex and then hand it off to our thread. While it's working, we can use the mutex to safely read the variable isFind to check the status of the thread. It's worth noting here that it's a bit weird, but we have to copy isFinished, so we don't hold on to it, the lock, longer than we need, because we don't want to hold on to that lock too long. We don't want it to be in contention. And we also declared our non-atomic bool is volatile to let the compiler know we will be modifying this variable on another thread. So again, calling lock on our std mutex will wait until we can lock, or just lock it immediately. So the other thread, if the other thread has the lock, we'll wait until that thread is finished. That way, it keeps our writing and reading to this variable safe. And the while loop is mainly there, frankly, in the case that the thread hasn't started yet, because it hasn't started yet. Lock would succeed, but isFinished copy, we would see false. Although really you shouldn't be using std mutex directly. There are wrappers for wrappers in C++, and in practice you should probably use something like std lockguard. But this is good for just an example. Anyway, atomics are very powerful, but are tricky to get 100% correct. Bugs caused by incorrect usage can be very difficult to manage. Besides that, we also have to share our atomic if we want to share the data before the thread is finished. So it's still a bit pain to share our data before we finished computing it. And std mutex has problems with all of its restrictions. It's certainly the safer option. However, it can be a bit slower in certain situations, especially if you spend a lot of time waiting to lock. Our implementation, you would have to share the lock, isFinished, and the data you wanted to return before the thread is finished. So that's some certain drawbacks. Enter std promise and std future. So more wrappers upon wrappers, but this gives us something. So thankfully, C++ provides a mechanism to simplify this for us. To start, let's modify our find primes function again to take std promise, which it then fulfills by handing it to the final value of primes when it's finished. just below, we create two promises, take their futures, and hand the promises to the thread to fulfill. You can then use the futures to safely get results. If the threads are not finished, get will wait until they are. Much like a mutex, it'll wait for that lock. If all the thread synchronization is, now we have all the thread synchronization handled in a very neat way. We can easily share the result by returning the std future, because the std future is basically a combination of the result when it's ready and code to prevent you from accessing it early. But even still, there are a few drawbacks to this. Mainly, we need to handle creating the promises ourselves. We also have to write our find primes function in kind of a weird way. We have to hand it the promise for one, and we can't have a return value, despite the fact that conceptually, of course, it returns something for us to use. That's where std package comes in. So let's take a look at our find primes function again. This time, we get to write it naturally. No extra parameters to track state and a proper return value. Then we can bind find primes to a std package task. A bind is the same thing as writing a very simple lambda that just calls it with those constant inputs. And then we can hand the package tasks directly to our threads to start work. Finally, we can use the futures we have in calling get when we're ready to get the results. So basically, the package task handles the promise. It gives us the ability to use very simple natural functions, and we can just grab the future from the task before handing it to a thread. And then when we're ready to read the results, we call get. If the results aren't ready yet, it'll wait until they are. So that's a very nice way to handle it. But of course, it's much nicer than anything we had before, but there's a decent amount of extra code to write, and maybe you're used to that in C++, but there is a way to shorten that, and that's what we have std async. Std async handles packaging a task for us, starting a thread to work on it, and handing us the future. So we get the future right away, it starts the task right away. It's a lot similar to what we've been doing, and it does it all in a single line. So it's very nice. We can compare this to our original code, which was using thread. Now we can see the new async implementation again. Of course, std async has some subtleties of its own, and we won't get into that too much as this is just a high-level overview. But it's worth noting that there are some cases where you would want to use std thread instead. And of course, the main reason of that, that doesn't get it too much into the weeds, is that you should be using a thread pool, ideally, because starting and stopping threads all the time, there's definitely a cost to that. And you can avoid that by having a ready pool of threads you can use. You could just hand the threads your package tasks and they can go at them. All right. So that has been our lightning review of C++11. We've gone over std thread, we've gone over atomics, mutual exclusion, std promise, std future, well as package task, and finally async. We've done it very quickly. And all of this and more comes from C++11. I think that's important to understand. In fact, a lot of this important stuff I didn't go over as well comes from C++11, again, particularly around atomics and mutual exclusion. However, having said that, definitely thanks to anyone who stuck around. I appreciate your interest in the topic. You've certainly earned a pat on the back for that. It's important to recognize the type of work that could be executed concurrently. I won't touch too much on that in the webinar, but I want to call that out as a critical skill. So now that we've reviewed the foundation, let's move on to what's truly new for C++ concurrency. Okay, so JThread is a newcomer to the standard, as in the class itself is new. Very similar to std-thread in its operation, except for a few key differences. One difference is that std-thread does not have join or detach called before the object is destroyed. You don't have to call join or detach before the object is destroyed. If you recall in our previous example, we always have to either join or detach our threads, even if thread has finished its work. So we'll take a look here. So it's a coding example we've seen before. We could take a look at the JThread implementation, and it shows that we no longer need any of those calls. JThread will join as soon as it goes out of scope for us, which allows the thread to be safely destroyed. It's mostly an annoyance to have to deal with that, because let's say you have another method to wait to know that your result is ready. You'll need to still call join, even if you know the result is ready and the thread is finished, because the thread finishing its work and the thread closing out are two different things. And the thread needs to be fully closed out before you destroy the thread object. So this just makes it a little easier. I've been calling attach frequently in my examples. In this case, I don't need that, and I don't need to do join. So that's quite nice. But even more interesting, std_thread supports a new feature in C++, which is the stop token. So the stop token is very nice. And to first take a look at it, here's how we can use find primes now with stop token. We need to rewrite our package task so that it can handle the std token. We can check. Okay, so let's rewrite our find primes function and again take an extra variable. In this case, the extra variable is the stop token, and we can just check it to see if a stop's requested. And if a stop is requested, we can break out and finish and don't do anything more. And we take a look at our code. We need to rewrite our package task here so that we can hand it the stop token to our find primes function. So we basically need to, our find primes function takes the stop token. The task itself took nothing before because it was bound to specific variables. And now instead of binding it, I'm going to create a lambda, and the lambda will hand the stop token, which is dynamic and handled into this. So basically, when I call jthread mythread and hand it my task, jthread is going to automatically detect that this package task can take a stop token. It'll automatically detect that, and it'll actually create the stop token and hand it to the task for me. So it handles all that for me, and all I need to do, if I want to actually use the stop token, is call request stop on my thread object. So it has methods to allow you to interface with the inbuilt stop token that it hands to your package task. So it's a little bit more verbose, but it's still rather simple. Especially if you're used to the syntax. If you're not used to the syntax, this might be confusing. That's what it does. And it basically allows you to stop or cancel a task. It's very, very, very nifty, really. All right, so let's move on. Next up, we have counting semaphore and binary semaphore. The best way to explain binary semaphore is to recall our code for std mutex. So let's take a look at the modified code. It's the same code, but now instead of calling lock, I can call acquire. To unlock, I call release. Acquire decrements the internal counter, which you can see I set to 1 on construction. If it can't decrement the counter, it will wait until it can, much like a std mutex. So what's the difference if our code is basically the same? Well, mainly the additional restrictions on std mutex. If the thread locks, if a secondary thread tries to lock a mutex, then I can't unlock it on a different thread. So the lock and unlock has to happen on the same thread. In fact, std mutex likes to be unlocked in the same context as the lock it was required, and that tends to be required these days too. There's a lot more to mutex, a lot more safety built in. So these differences make std mutex better for its main use, which is protecting data in a multi-threaded environment. But that's not to say that it's bad in all cases to use semaphores to handle resources. So let's look at counting semaphore. Counting semaphores let you acquire a lock more than once before it starts to block. So it's basically a binary semaphore is a specialization of counting semaphore where the max counting is 1, so you can only be 0 or 1. The counting semaphore lets you set higher limits. The behavior of it makes it very useful for handing out a finite number of resources. We'll still need to protect access if we see we've got. So our count lock, that's going to be our counting semaphore. I didn't have room to show all the code where this stuff is declared. So count lock is our counting semaphore, and you can see that we acquire count lock whenever we get this big reusable object from our cache. And whenever we free big reusable object from our cache, we release a count lock. And we still have our mutex to protect access to our resources, which are our actual, our vector of these big reusable resources. So basically what will happen if I try, let's say I have 4 resources to give away. Once I've given away 4 resources, that means I've acquired count lock 4 times. The 5th time I try to acquire count lock, it's going to hang basically right here until it can acquire. So until someone releases a count. So that's basically how it can protect access. So it can allow you to stall on waiting for more resources. Of course, something like this is dangerous. You don't want to. try to get like, oh, well, I need 5 resources in this one thread in order to work. Well, of course it's going to hang, and no one's ever going to release those resources. So that's something tricky you need to keep an eye out for. But this is just a basic example to try to show you how you can use count lock in a useful way. Okay, and now I want to talk about std latch and barrier. So std latch and barrier, they're a lot like a counting semaphore in that std latch, but there's a couple of main differences. So the main differences is std latch can only be decremented. You can't increment std latch anymore. Std barrier can be both incremented and decremented. And in particular, they're useful for coordinating threads. So here's a very, very simple example. If I have this function, and I mean to call this function in a thread, but I want it to wait before it starts. I want it to get ready to go, but I don't want it to actually start until a certain time frame. I get handed a latch, and it can just wait on the latch. And then in my main thread, when I release the latch, the thread is ready to go. So that's mostly what it's used for. It's for signaling, but it's a one-time signal. It can't be incremented again. So this, we need to make sure to not just use the same latch over and over again, because we can only decrement it. So that's its main use. You can signal to your threads when something has happened and use it as synchronization primitive, particularly with longer threads. Let's say you've got frames in a video game and you want to synchronize everything. The only problem with latch, like I said, is you can't increment it, you can't reset it. And that's the difference with std barrier. So for example, if you wanted to sync a thread to happen after multiple threads have finished, like let's say you're rendering a video game frame and you have the physics on one thread and whatever. Now, realistically, it's hard to do that. But let's say you do have the physics, sound, and all the stuff on different threads. And you want it to synchronize, and when everything's finished, you want to run a new thread, which is to present that frame now that it's finished rendering. So you can use a barrier to do that. You can have a thread waiting on a barrier, and the barrier can be decremented by all the different threads. And once let's say I have 5 different threads, then the barrier could have a count of 5. And once they've all decremented, the final thread can run. The interesting thing with barrier is it also provides an onCompletion function, so that you can use the onCompletion function to do something once that reaches 0. So for example, you could set the barrier back up to 5 for the next frame. Now, personally, I had some bugs with this when I was implementing it on my own system. That kind of happens with these newer implementations. I'm guessing it's user error, but I won't show a code example because I don't want to show something that I'm not 100% sure is at least correctly compilable. Anyway, so it's useful for a thread waiting for multiple tasks to complete. So we've gone over a lot of C++11 and some C++20. There's certainly a lot more that I would want to talk about here, and I think that maybe I could do a follow-up sometime to give more advanced topics, to talk about memory ordering, to talk about that kind of stuff that you need to pay attention to when you're multi-threading. And maybe different examples of how you can intercommunicate between threads and play between them. And that could take a lot of time. So we'll leave that to another talk. But we went over JThread and its new enhancements over thread. We went over counting semaphore and binary semaphore and how they can be used to signal between threads. And we talked over latch and barrier, which is basically very similar to a counting semaphore, but with a more specific use. Much like bool might be an int in a lot of cases, stating bool is helping state your intentions, which is an important thing in development. And why so many of these different things exist when they're reimplementations of the same thing. Okay, and I think I'd be amiss to not go over concurrency and parallelism and the difference in a talk like this. So of course, concurrency is tasks which overlap in time. And of course, if you have a single-threaded computer, concurrency was one of the first things that allowed us to have 2 tasks running at once. It would just, the operating system handles swapping between the tasks and letting each task have some CPU time. And parallelism is different than concurrency, but similar in the way, in parallelism is more hardware focused. So you're executing multiple tasks on a multi-core CPU. Multiple tasks are actually happening at the same time. So with concurrency without parallelism, you have the OS switching between tasks on a single core. And with parallelism, it's just a multi-core GPU executing tasks simultaneously. Technically, there's a difference between these words, and I'm going to go ahead and mention it here. But it's a bit of pedantry. All right, so we're ready for the live Q&A. I'm sure we have a fair number of questions, or maybe some people were just too overwhelmed at the speed that we went through to have them, but let's get started.
All right.
Okay.
Thank you, Chris. I'll start here with a question that came in. If we can't reinitialize the stood latch, in what scenario should we use it instead of stood barrier?
When you only need it once. So if you're firing off a thread that's going to complete and you just want to know when that thread is, you just want that thread to, it's not a reused thread, basically. If you're not going to reuse the latch for something that happens once and isn't going to happen again for a while, that's generally the answer. If it's not something, if it's something you want to coordinate that only happens one time with your setup, or even one time per frame, there's ways you could write it either way. There's so many ways to skin a cat in C++. But if your use case is that you only need the thread to wait once, then latch is your answer.
Okay, thank you. So here's another one. Is it okay to use a thread for something very short? For example, like 100 milliseconds or less, that could be run on the main thread without too much impact. Is it bad? Is there overhead using them for small work?
Yeah, I wouldn't do that just because there is a lot of overhead. If you have a thread pool, the overhead is reduced considerably, but even then it's a good idea to not do that. One thing I would suggest though is if the task usually doesn't take much time, but sometimes it takes a long time, then I would run that even though you've got a bit of an overhead, because it tends to, it'll help normalize in the end, and you'll have a more responsive UI, for example. Even if you don't use that time for anything other than just pumping your message queue, that's still quite valuable to users.
So then along those lines, how do you judge balancing the workload? How do you split up the work among threads? This person says you didn't do it equally. Was it just guesswork, or are there ways to calculate and assign work?
I personally would just benchmark it. That I think that's really the only answer. It can be difficult to assign to balance your threads properly. I will say that it's less of an issue once you have much longer tasks. So for example, our parser, when we run through a bunch of files, we don't have to worry about balancing it as much, because let's say parsing takes a whole minute, but the difference between parsing the longest files and the shortest files is only a couple of seconds. Then at most we're looking to save a couple of seconds by properly balancing everything as perfectly as possible. So the situation is mostly important when, let's say, you have 8 or less tasks that you want to run at once, because let's say most computers have a lot of cores, you might just run all that at once, and then the completion time is just the longest task. So in that case, balancing makes a big difference. It can make a big % difference in the total time it takes to complete.
Awesome, thanks. Just had another question come in. Is it suggested to create several threads, same task, different data, and leave the main thread empty?
It depends on what you want to do with the main thread. If you have other work you can do, it's fine to just, okay. It depends what you're writing, but generally you don't want the main thread to ever halt. And the reason is because when that happens, then your UI halts. Even for something as basic as just a Win32 window, if you stop pumping the message pump, when user clicks on it, Windows is going to think you're hung. So really, you should never be hanging the main thread. And even if you're just spending your time, pumping the message pump, that's totally appropriate. So I wouldn't hang the main thread very frequently. It's definitely a good idea to use threads for any long-running tasks, and spend that extra time keeping your UI active.
Got it. And then someone asks, are there lockless containers that are thread safe, or that can be synchronized across threads without locking?
Yeah, lock safe, that's basically using the atomics like I showed. There are certainly some issues with atomics. There's some complexities there where you need to be aware, because the way I use the atomic was okay, but in certain other cases it's not okay. For example, let's say I have 2 threads that are checking the atomic, and then they both check the atomic, and they both try to write to the atomic. I can see that situation happening. And so basically atomics aren't enough to really protect you in all these situations. So you do need to be very careful. But there are certain ways, like I said, using, for example, the signals that I showed earlier, with the counter, for example, the semaphores, you could use that. But generally, if you're trying to protect access to something, mutex will kind of take the worries away. It'll make sure that the memory is aligned correctly, it doesn't get reordered. It'll make sure that only one thread can actually pull the lock at a single time. You don't really get that kind of level of protection with atomics.
And can you just briefly revisit what is an atomic?
So an atomic is something that is guaranteed to happen without your thread getting suspended. So basically, let's say I was writing an integer, and let's say for some reason it took me a little while. It took more than one CPU instruction to write the integer, and my thread got suspended midway. That can happen. And maybe I start reading a variable just as another thread is halfway done writing to it. And if that kind of thing happens, and that kind of thing can happen, you basically have to assume it can happen on any variable, no matter what. So what atomics are is they provide a guarantee that that situation will never happen, that you'll never have the situation where another thread will see it half written or something like that. So it's something that happens in generally run one CPU instruction. And getting into more detail, it freezes certain operations on the hardware to prevent you from needing to do that, to handle that synchronization. It's less weighty. Writing to atomics, even though like a mutex generally would use an atomic as part of its implementation, mutexes are slower than just atomics because mutexes work at a different level. They're more of a kernel level object, whereas atomics are just a user mode thing. You don't require any switching. But like I said, they're less protective.
Got it. Thanks. We have some really great questions coming in. This is a little bit of a fun one here. In game development, what are some of the most useful or commonly used applications of multi-threading in your opinion? And in which cases would you recommend it be avoided?
That is a really, really hard one, but the obvious ones are stuff like audio. Audio you can do on a multi-thread. A lot of people nowadays will load the frame buffer up using multiple threads, or I'm sorry, load the instruction queue using multiple threads. So for example, you could have multiple generators of rendering instructions and then combine those instructions into one before passing it off to the GPU. So for example, a lot of the code in video games is done in such a way that the code to generate rendering instructions is the same as the code kind of to update the objects. So if you can do that in multiple threads, and you can do multiple object updates in multiple threads, and combine the instructions that get generated later. That's a really common one, multi-threaded rendering. You've probably seen it in a lot of games. It's a toggleable option in like the source engine. But it is really tricky because a lot of things need to happen lockstep. For example, with physics updates, you need to be very careful, where the sound comes from. It all gets very, very tricky and interlocked. A lot of things are very interlocked. And the best way to think about it is try to just think about how your data is processed, what data needs to be written, what data can be held constant for a while, what data needs to be read. Instead of thinking in terms of object orientation, you could be a little bit more data oriented. At least in your thinking about threading, it tends to be much more valuable when it comes to determining what can be threaded and what can't.
All right, a few more here. When would you use stood thread instead of JThread?
Personally, I would just always use JThread. I just like JThread. I think it prevents it. It will cause your program to straight crash if you use a thread and then don't join or detach. So this can prevent crashes. Of course, maybe you want that crash because you intended to do that. But in the case where you just don't want to handle that, like for example, in the cases where joining is redundant, because you already have another mechanism to know when your variable is ready to read, such as a promise or a future. then it's really just an unnecessary call, and you can just avoid it, or avoid having to also call detach. So it's quite useful there. But more than that, I would that's the reason I would probably use it exclusively. But besides that, it also has this very nice feature where you can it's got the built-in support for that stop token, and the stop token is actually really nice. You don't need to use it. You can just hand JThread something without the the parameter to take a stop token, and it'll very happily take that too. But if it sees that your function, or whatever your multi-threading, that function that you hand it, or the package has room to take a stop token, it'll hand it to you, and it'll manage it for you, and it'll let you interact with it, which is very nice. So generally, I would think of JThread as just the successor to Thread in a lot of ways.
All right. In case we have a lot of data to handle at the same time, is there a limit to how many threads we can use safely?
Not really.
All right, that's an easy one.
I mean, there's no and yes. I mean, you'll run out of memory eventually, but you can use a crazy amount of threads.
Okay, could you tell us more about the STD counting semaphore drawback?
So it would have the same drawbacks as an atomic for the most part. If we go back to STD counting semaphore, I can't actually use it to protect this resource or anything like that. The best I can use it is kind of a signal. And that main drawback, it's the same as atomic. It's basically, you can think of it a lot as an atomic, like let's say an atomic integer that you can increase and decrease. And it has a bit of built-in logic to wait if you try to decrease it when it's already 0. That's basically it. Whereas mutex is much more powerful, much more restrictive, and meant to protect access to resources like this. So even in the case that we use this counting semaphore to hold when we try to take more out of the bucket than we have, we still have to protect the bucket. So that I would say is the main drawback. You just need to be careful not to use it where it's not intended.
Someone said you mentioned that you sometimes should use a thread pool. Is there any functionality in STD for creating a thread pool?
Not that I know of, but we'll wait till C++ 22 or whatever, and I'm sure it'll be there. Until then, though, it would basically be an array of STD threads, right? That's how you would create a thread pool in C++. And you could hand those threads your work.
Yep. More general question here. What are the benefits of multi-threading on single core architecture? Is multi-threading without parallelism, does that make sense?
Yeah, it's critical, as a matter of fact. Without that kind of support for multi-threading on single core processors, you would never be able to do two things at once. So you couldn't play music while looking, while watching a video or playing a game. Now, single core CPUs can still do all that. And the way they do it is basically the way that the operating system handles the multiple threads is it just switches between the different threads on the single core. So it just does a lot more context switching. And it does that frequently in order to make it feel real time. So it's very, very important, and even on a single thread CPU, it's important to have this kind of threading.
Okay. Does memory allocation in multiple tasks lead to issues as the memory allocation is done by the OS? Could that result in a bottleneck?
It can. The main problem is if you're memory allocating for types, so the allocation for the different threads and stuff is very fast. You shouldn't worry about that too much. And besides, you should be working from a pool, so the allocation has already been done for you. But if you're talking about allocation of the stuff that the actual thread needs to handle its work, then yeah, that can be a bottleneck. And as a matter of fact, inside of our own product, we use a custom allocator to handle that stuff because it can be very expensive. To just, let's say, oh, I need to allocate thousands and thousands of strings now for all these different threads to operate on. Yeah, that could be a big bottleneck. And so it's the same bottleneck that you would have if you just tried to allocate a bunch of those resources at once. But yeah, so if you come across that bottleneck, and it is very real, custom allocators helped us quite a bit. But modern Windows has pretty good allocators built in, but still, that could be an issue. And essentially, fixed size allocators were the answer for us. So you need to be, something that can allocate much more quickly. Because yeah, now I need, as I would need this many allocations for one instance of this. Now I'm running 10 different threads of it, 10 times as much time is being spent on startup. It's not the thread's fault. It's just that you're doing more allocations at once because you're doing more work at the same time. But allocations themselves aren't inherently multi-threaded.
Thank you. All right. Someone asked, what do you think about conditional variable in comparison to semaphore or latch? When does it have an advantage?
So again, a lot of times the difference. So I didn't have time to touch on conditional variable, but it's very similar again to think of it as an atomic with the limited with all the caveats that atomics have. It's extremely useful as a signal between threads, and it's basically in a lot of ways it's the same thing, but the difference is conceptual in how you use it. Like I said, a lot of people use int as their bool, but should they? No. Because there's conceptual differences, and that's the main reason. It's the main difference compared to, like, let's say a latch. Of course, a latch also, I believe conditional bools can be reset. So latch can't do that. Latch can't be reset. It only happens once.
Which of the mentioned locking mechanisms would you use to prevent reentrancy vulnerabilities?
Mutex. It's super duper strong. You pay the price in time, because in order to grab the lock on a mutex and free the mutex and all that, let's say it does need to switch context on your CPU, but it is incredibly powerful. And so if you need to be sure, and you need to be sure that it is going to get weirdly reordered or anything unexpected is going to happen, use your mutex. It's very, very, very strong. So I would use that.
Awesome. Thank you. We have a few more here and then we'll wrap up. Is the volatile keyword still critical in modern C++ compilers for multi-threading to be accessed from different threads?
That's a really good question. And in most cases, the answer is no. As a matter of fact, in my talk, in all the coding samples that I showed, I only used volatile once. And that was when I was using a regular bool. And strictly speaking, that code will work without that volatile. It's basically just a hint, just like inline is a hint that, oh, maybe you should inline if you want, maybe, even though it's just going to not listen anyway. It's just a hint to prevent it from like optimizing it away and never actually checking the memory for some reason, because that variable can get updated. I would still use it in some cases, but you don't need to put like, you don't need to have like a volatile atomic, if you're, or you don't need to declare your mutexes as volatile. All that's handled. So only if you're using plain old data, and even then, it's just a hint.
Got it. Thanks. In parallelism, if different cores are involved, how are task completion and synchronization handled?
Well, so that's kind of where you can use the signals I was talking about a little bit later, like the semaphores, to synchronize tasks. But if you're talking about in general how they get handed to the actual cores, so that is something that you don't actually worry about. That's something that C++ hides from you. How those threads get assigned to cores and stuff like that. You do have some control over that. I don't think that you have control over that through thread. I think that you would have to have operating system, dependent. So, for example, create thread, I could have more power than by using std thread. But create thread is a Win32 call. So I could maybe have a little bit more power over what cores it's assigned to and stuff like that there. But creating threads and stuff like that is agnostic to cores in C++. We don't need to know anything about that. It could be a one-core computer, CPU, and then Windows is going to handle that for us. Windows is going to handle scheduling those threads and swapping them out when necessary. So we don't need to worry about that, thankfully. If I understood your question properly.
I think so. So let's do two more. Someone asks, if I have a heavy task and then I'll put it in another thread to do it, how should I choose between stood thread and stood async?
Okay, so there really is, so generally stood async is just the shorter, more like simpler version of stood thread, because it starts a stood thread for you, it creates the package task for you, it hands you the future, all stuff that you would have to do manually if you use stood thread. There's one drawback, and it's a technical drawback, and the destructor for the future is going to block. And I don't know if that's going to be an issue for your code or not. Basically, it might be more difficult for you to return before it's finished. My answer to that is actually just use, well, the real answer is use a thread pool. But if you're just gonna throw out a thread every now and then, and that you don't just want to use async, or you want to just implement it right there, just use async. Use async, and if you find any issues where there's this technicality where, oh well, maybe it's not returning as quickly as I want because it's waiting for this thread to exit, then just be careful about how you're using your future. It's a very technical thing. It's I wouldn't worry about it too much unless you kind of hit it. But it's something to keep an eye out for.
Got it, thanks. Before I read this last question, I just wanted to say thank you to everyone who submitted questions. We have had so many good questions. I've tried to get through all of them. If I wasn't able to get to yours, my apologies. But that does lead into this last question. Several people have asked, do you have any online resources or exercises, or maybe there's a book that you would recommend to learn more about these threading functions, to develop more hands-on experience with?
Yeah, so the interesting thing, like I said, is modern concurrency in C++ is pretty old. It's from 2011, believe it or not. Basically everything I talked about is from 2011. So there are books, and even older books on C++ concurrency that would give you a very good, strong sense of what the minute technical differences are between these little things, and how to use them effectively in various different ways. One of them I can call out right now is the C++ Concurrency in Action, Practical Multithreading by Anthony Williams. That was a book written in 2012, I believe, which is just a year after this, C++ 11 was ready to go. And it basically covers C++ 11 in high detail. So it's quite a bit there. But if you want to be a true expert in multithreading, this book is where I would start. It'll give you a tremendous amount of in-depth understanding that you won't get from reading the standards and even just using it on your own. It's a very, very good book. And like I said, even older books are still modern, because C++ 11 is still modern. The stuff that they added in 20, we went over a few things, nothing game changing, nothing even close to what was added in 11. So that's where I'd start. C++ Concurrency in Action by Anthony Williams.
Awesome. Thank you for that recommendation. Well, we are coming up on the end of our time. So again, I just want to say thanks to Chris for putting together this great content. Thanks to everyone who attended. Just to reiterate, we will have a recording of this full presentation available. You can also get the slides from the handouts section of GoToWebinar. We appreciate you all for your time, for your attention, and your awesome questions. So thanks everyone again. And we hope to see you at the next one of our webinars here in a couple of days. Thanks everyone.
All right, bye-bye.
Thanks everyone, goodbye.